let's consider phase diagrams. Here we're going to consider a plot of the pressure versus the temperature for a substance. And we will get areas and our plot will look something like this. And what we have along these lines are where two phases are the same stability. We say that the chemical potentials are equal, but you can think of them as being equally stable. We have on the left the solid phase, in the middle the liquid phase, and here we have the gas phase. So away from the lines, like in this area, the solid phase is more stable. In this area, the liquid phase is most stable. And in this area, the gas phase is most stable. If I'm on the line here, if I'm on the line right there, that means that liquid and gas are equally stable. And so on the line, I will have boiling of the liquid. If I'm at this point right here, solid and liquid are equally stable. So I could have solid and liquid existing simultaneously, and I would have ice floating in liquid water, for example, and the ice wouldn't be melting. If I'm here, at this point, this is going directly from solid to gas. This is sublimation, so I have solid and gas equally stable along the line. So if I'm in an area, say I'm in this area right here, just in blue so you can see it. So I'm right here at a particular pressure and temperature. Liquid phase is the most stable at this point. So this would be like having a water at room temperature in a beaker. If I raise the temperature, so I'm going to increase the temperature, I'm going to keep the pressure constant, just increase the temperature, I'll get to this line, and now liquid and gas phase are equally stable, so when I get to this line, I'll hit the boiling point. And if I keep raising the temperature after that, then gas phase is most stable. So in these areas, you can see the phases that are most stable on the line. They're equally stable between two phases. Now there's one point where all three lines converge right here. So at this point, we have solid, liquid, and gas being stable at the same time. And this is called the triple point. So this is where solid, liquid, and gas are equally stable and coexist. We also have another point here where the gas-liquid line stops. And this is called the critical point. Now say we have a gas, and I'll do this in red. Say we're right here at this point, and gas phase is most stable. Then we just keep the temperature constant, but we're just going to raise the pressure. So we start raising the pressure. So we're going up in pressure. Then we go up in pressure, then we hit this line. So now liquid and gas are equally stable. And if we keep raising the pressure, then we'll go into the liquid phase. So we can liquefy gases by just raising the pressure on top of the gas. And a good example of this, you've seen like LP gas, like you have propane deliveries to homes where natural gas is not available. Then you have this big truck, and it's LP stands for liquid propane. Normally, at 1 atmosphere pressure, room temperature, propane is a gas. but under pressure you can liquefy propane, and liquid is much more dense, and you can put more into a tank, and so you can haul more, so it's more economical to liquefy it. So you can liquefy gases under pressure. However, if you're here and then increase the pressure, this line has stopped, so you can no longer get to the liquid phase. And so you don't liquefy the gas past the critical point. What you do is form what's called a supercritical fluid. Now, you're increasing the pressure, so the density of the fluid is high, but it's not a liquid. It's expanded to contain the whole volume like a gas, but supercritical fluids can have some strange properties. One strange property of supercritical carbon dioxide is that it can dissolve substances like organic chemicals. It's used to decaffeinate coffee. So these are the areas on a phase diagram, and you can see how you can change the pressure and temperature, go from one phase to another, and by crossing these boundary lines. One interesting example is, say, the phase diagram for carbon dioxide. We have solid, liquid, and gas. So if we go over here to where the triple point is, you can see that liquid phase, this liquid area, doesn't exist except if you're above the triple point pressure. So for carbon dioxide, the triple point pressure is 5.1 atmospheres. So the liquid phase does not exist below 5.1 atmospheres pressure. So if you're at sea level, 1 atmosphere pressure, and you have carbon dioxide, you can have carbon dioxide solid. So down here at 1 atmosphere pressure, so say I'm here, if I raise the temperature, then I go directly from the solid to the gas phase. So this is why it's called dry ice, because at sea level, 1 atmosphere pressure, then carbon dioxide never melts, never forms the liquid phase. It goes directly from a solid to a gas. That's called sublimation. So it's convenient. Another example of using phase diagrams is freeze drying. So say I have the water phase diagram. Let's look at the phase diagram of water. The triple point, the pressure here is about 6 torr. So remember, there's 760 torr in an atmosphere. This is well below 1 atmosphere, and this is about 0.01 degrees centigrade. So close to 0 degrees centigrade and very low pressure. So say I'm have ice, and I don't want to melt the ice. Say I have beef stew. And I want to lighten it. Well, the water's heavy. So I want to get all the water out of my beef stew. Well, I could boil it, boil the water away, but as I boil it, I'm also cooking it more and more and more. And the more water that is evaporated, the higher the temperature I have to go to keep it boiling, and so it just burns. You can't get the water out and keep something edible by boiling. But if I freeze my beef stew and then put it under a vacuum, so I get below 6 torr, now liquid phase can't exist, and I can pump by lowering the pressure. So say I'm right here. So this is, say, 1 atmosphere. And I'm at solid phase. So if I just reduce the pressure, this is pressure and temperature, say if I just reduce the pressure, I will cross the solid gas boundary. So this is before liquid phase exists. So I'm down here now, and so now I'll go directly from solid to gas by lowering the pressure on top of my frozen beef stew. So I just pull a vacuum on top. So now gas phase is more stable for water. So the ice here, this is frozen, so ice will go directly to gas without melting. So that way I can get rid of all the water in my beef stew without having to heat it and boil it and cook it more. I can just go directly to the gas phase by reducing the pressure, keeping the ice frozen. That's another way to, you have coffee, you have instant coffee. You take coffee, brew it, freeze it, put it under a vacuum. All the water goes directly from ice to gas, so you get rid of the water. Then when you want to reconstitute it, you just take the solid crystals, stick them back in water, reconstitute your coffee, or you can reconstitute the beef stew by just taking the solid that's left over once all the ice has gone to gas phase. It's much lighter. You can carry it in your backpack. And then when you want to reconstitute it, just put water back in there, heat it up, and you have good tasting beef stew.